second session of today's STTP. Now I request Dr. Harmeet Kaur Khanuja ma'am to introduce our speaker. Khanuja ma'am, over to you.
Yes. Thank you, sir. So today we have our expert speaker, Mr. Shadab Hussain. He is data scientist. His specialization is in quantum machine learning, and he is a full stack data scientist and a quantum computing enthusiastic with around 3 years of experience in analytics and building end-to-end ML pipelines on cloud using agile framework. He also has experience on quantum computing using Qiskit and founded Building Quantum Computing India community. He is specialized, he has many specialties actually. So mainly he specialized in data science, machine learning. He has good hands-on on Python, R, SQL, neural networks, AI. He's innovator, researcher, and best part like he has lot of knowledge in quantum machine learning, which is just coming up area. So we welcome Mr. Shadab Hussain to take today's session and just enlighten all the participants to gain maximum outcome of it into the research areas. Many of our participants, they are doing research in this area. So of course, we are going to get guidelines. We are going to get certain directions. So how, what exactly, the research is going on and how we can come up with this, this exclusive AI ML domain. So over to you, Shadab sir.
Thank you, ma'am. Thanks for the invitation. So we will start with the session. So before starting, I will just set a few context what I'm going to cover in today's session. I will introduce you to the quantum computing, the basics of it, and why quantum computing is in hype these days. And then slowly we will move towards what all packages we can make use of if you are trying to prototype any of the solutions using quantum computers. And then we will also see one of the hands-on using either Qiskit or Tensorflow. So that depends upon the timeline which we can pick up. Okay, and along with covering all these topics, I will also talk about few of the international communities which are available. If any one of you are interested in collaborating with the researchers or learning more about quantum computing from the basics to the advanced level, I will suggest do join those communities. They keep on hosting multiple events. So it will be a good start for you. And as ma'am was telling, yes, there are huge research opportunities available in this field, not just in quantum machine learning, but quantum mechanics, quantum physics, noise correction, error algorithm, all these areas. There are a very good research work going on, not just in India. In India, if I talk about, there are research institutes like ISRO, DRDO, and then academic institutes like IIC, Raman Research Institute, IITs. All these are actively involved in the development of quantum ecospace in India as well. And government has also funded a good amount of, they have also poured a good amount of money in this, and they are also willing to take India with the level where other countries are moving these days. Okay. So if you want to follow up, then there are websites like, CDAC is basically the one of the collaborator with the government of India as well. So look at what research work they are doing, and it will be a good head start for you all. So I will name few of the professors and research institutes where actively people are working on that, and they are producing IP, research papers, patents, and all. Apart from that, there are many other places outside India as well, like especially the Europe, US, and Australia. These are the hubs for quantum computing. And almost all the government organizations are pouring money in billions of dollars to advance the quantum technology. Okay, so without waste, let's start with today's session. I'm sharing my screen. Let me know if you can see it. I hope it's visible to you all. So so before starting, any idea what is quantum computing and how it can, why do we need quantum computing first of all when we already have advanced classical systems with GPUs, and now few systems are coming with TPUs as well, like Google is giving TPUs on cloud. We have supercomputers already developed, right? Then why do we need quantum computers now? Like, what is so big about this? Any idea? I will keep checking the chat. So if you have any questions, you can ping me there. Okay. Yeah. So quantum computing is, I mean, the work in this area is going from decades. It's not something like which has just started 3 or 4 years back. In like in 1990s or 1980s, also a good amount of work was happening. But with I mean, as every one of you remembering, right, the machine learning algorithm and all were also coming around 1980s or 1990s. People were able to develop those algorithms, but because of the limitation in the hardware, they were not able to program that on computer systems, and people are not able to make use of it. But those algorithms, like most of the algorithm in machine learning, is still what people are using. Came in 1990s or the early 2000s, right? And even neural network also, that was also in the uh, like in the previous decade, basically, in the previous to previous decade. But with the advancement of the systems, the when the systems were able to process uh, more and more information, and they were becoming more powerful computationally, we started seeing the implementation of those machine learning and deep learning algorithms, and gradually industry also started adapting it. And nowadays, in all the sectors, in all the domains, people are making use of machine learning or deep learning in some or the other way. Hardly there will be any area in which people are not making use of it, because everyone is relying on data and what insights and prediction they can get out of that, right? So that's the most important part here. Just 1 second, I'm getting a call. Just sorry. Hello. Yeah, sorry for, I mean, I got some important call and I had to pick it up. Yeah, so with that advancement in those computing systems, right, people were able to make use of machine learning and deep learning. And if I talk about sectors in which it is getting used, I hope everyone is already aware, like whether it is fintech or healthcare or retail or travel industry or drug discovery or even disease prediction, surgeries, everywhere people are making use of it, where some sort of advanced machine learning and deep learning techniques are getting used. If I talk about surgery or disease prediction as well, the people are making use of reinforcement learning or deep learning. Reinforcement learning is getting used in a way that people are training robots and programming in such a way that doctors can perform surgeries remotely with the help of robots, right? It's still like those technologies are under development, but that is also one of the thing people are looking forward to. And robotic surgeries are already in practice these days. In good hospitals, you will find that. So with these advancements, right, quantum, if I come to the quantum computing, previously quantum computing concepts were also existing. Quantum computing is basically based on two of the principles of quantum mechanics. These are called as superposition and entanglement. Okay. So by making use of these two properties of the quantum mechanics, with the help of quantum computers, we can perform certain computationally very expensive operations which are like impossible to solve on classical computers in few seconds only, or in some reasonable time, okay, which can even take 1,000 or 10,000 of years to solve on classical computers. If one of the use cases if we talk about here, right, uh, we all know the encryption techniques, right? How the information has been encrypted over internet and or on a desktop, so that it cannot go in some unauthorized hands, and people cannot make use of like misuse it further, right? So there are many encryption algorithms. Very importantly, which we use is RSA 2048 encryption algorithm, which people do use over internet for sharing for encrypting the information, right? So Peter Shaw, one of the scientists who gave Shor's algorithm, I don't know how many of you are aware of that. So in Shor's algorithm, he demonstrated an algorithm which can break the existing RSA algo. Like if that algorithm has it gets broken, right, all the information over internet it will be over like understood at all, and it can, if it falls under some evil hands, obviously it can be used in any wrong way, in any improper way there, right? So, I mean, not just our data, but even the confidential data which governments are holding, the military services data, the communication which is happening over satellite or over network, everything can be hacked very easily with the breaking of the RSA encryption algorithm there, right? And it has been demonstrated that using so Shor's algorithm, he gave an Shor's basically he gave an algorithm which can break the RSA algorithm in much faster way in comparison to the classical computers. So Shor's algorithm basically, I mean RSA algorithm basically works on the factors of the given odd number. If the number is very large relatively, finding the factor of that number will be very much time consuming. Okay. So, because of the limitation of the hardware or even the supercomputers we have, people are not able to break the RSA encryption yet. But using quantum computing and using the Shor's algorithm, what he suggested, like step by step to solve that, with more, I mean, people have demonstrated few of the use cases of the breaking of the RSA algorithm. Let me show you that RSA breaking using quantum. So that was even in the news as well, that 20 million qubits would be required, and in 8 hours, 2048, the RSA can be easily broken, right? And with more advanced quantum systems, like if we have more and more number of qubits existing in that, all these security of the information can go at a toss, right? So that's why even everyone is concerned these days. Like if uh, more advanced quantum systems are coming in next decade or next 5 to 10 years, there is no fixed timeline how fast this research work will go on. But if that is happening, then how to tackle that? So people are working in the areas like quantum cryptography and post cryptography, like that. So this is one of the like use case which where quantum computing is getting used. Apart from that, there are many other places like quantum machine learning, then or other computational expensive task also. It's people are demonstrating the efficiency of it, basically. Okay, so coming back to what is quantum computing, right? So quantum computing basically make use of the properties of quantum mechanics like superposition and entanglement. And using these two properties, it performs computation. Okay, and the whole combined system is considered as a quantum computer. So the next question would be what is superposition and entanglement, right? And before going to that, let's see a definition which was being given by a Microsoft researcher, David Riley. Like a quantum machine is a kind of analog calculator that computes by encoding information in the ephemeral waves that comprise light and matter at the nanoscale level. So superposition and entanglement property, which we are going to see here, right? So these two properties plays a major role in which gives a computationally runtime advantage to the quantum computers over classical computers. All right. So the very next question would be, what is superposition, right? And what is entanglement? How do we understand these two concepts? Okay, so just to explain you these two basic concepts based on which the whole quantum computers are built on. Superposition is something like when, if we take an example of music notes, right? When one music note is playing and simultaneously if you play another music note as well, so the sound which we will be hearing from our hearing sense, right, the ears, that will be the overlap of both the musical notes, right? That will be the overlap of both the musical notes. So that phenomena, the end sound which we will be able to hear when two or more musical notes are playing simultaneously, is considered as the superposition basically. Okay, so this is like one of the fundamental principles of quantum mechanics. And the musical tone which we hear also, right, the sound energy also travels in form of waves only. So there the frequencies are getting overlapped or superposed with each other, right? Which is which in which when they're combined are producing a uh, new state, you can say, which at the end we hear. Okay, so the same superposition is this form in quantum state is a valid state in quantum in quantum, and using this we can store a huge like a good amount of we can demonstrate basically multiple states at once. So I will come to that as well, like how, like in classical computers we have the information stored in bit formats 0 and 1, and how in quantum computers we have information stored in qubits which can have any value in between 0 and 1 or 0 or 1. Okay, so to explain superposition, let's take one example. Schrodinger experiment you all would have gone through. So Schrodinger is one of the famous scientists. He did an experiment with his cat. What he did was, like, he locked his cat in a box or in a room, you can say, with in a box with a uh, bottle of poison in that. Okay, so if you have to find out whether the cat has drunk that poison or not, has, I mean, if not, then how we'll find out? If yes, then how we'll find out? If the cat has consumed the poison, then whether it is dead or alive, that's the question he wanted to answer. Okay, so as a normal human being, without opening box, can we find out whether the cat is dead or alive? No, right? It can be dead or it can be alive, but the exact information we will be only able to get when we open that box and see from our eyes whether the cat is alive or dead. If cat is alive, that means she has not consumed the poison. If she is dead, that means the poison has been consumed by you. So yeah, so based on the same phenomena, uh, superposition also works. So there is a video also, like which is being given by Microsoft. Let's have a look at this one as well. So in this, in very brief, they have explained about superposition experiment here. Okay, let me play this.
Killing time with another online cat video, eh? And to think other people are busy figuring out how to use quantum computing to overcome global hunger, prevent pandemics, and even reverse climate change. Fortunately for you, this is no ordinary cat video, and I'm no ordinary cat. I'm Schrodinger's cat. Not familiar? Well, you see, Dr. Erwin Schrödinger, born Vienna 1887, he came up with a thought experiment about quantum mechanics. All you need is a radioactive atom, a Geiger counter, a hammer, a glass tube filled with cyanide, and a cat in a steel box. I guess this is what people did with their free time in the pre-cat video era. Not weird at all, Erwin. When the atom decays, it releases radiation that sets off the Geiger counter, which triggers the hammer to break the tube and kill the cat who never did anything wrong except spray the rug that one time you were at the lab all night. I mean, simple enough, right? Wrong. You know nothing about superposition. It means that the electrons in the atom are actually in multiple states at once. So the atom is both decayed and intact. Therefore, the cat, aka me, is both alive and dead. Until, of course, you open the box and observe only one reality due to your inherent limitations as a human being. Back in the day, an understanding of the movement of electrons helped create the silicon chip that powers this traditional computer, and an understanding of superposition.
Yeah, I will pause here. So based on this, basically the concept of superposition was given. Like, I mean, this is what we call a superposition. And based on these properties, quantum computers are built actually. So superposition is a combination of states we would ordinarily describe independent of each other. Okay. Next important property is entanglement. Entanglement tells us that, I mean, this is a physical phenomenon that tells that there is a relation between two or more particles existing out there. And if those particles are related to each other, then if you make any changes in the particle A, then that will disturb the particle B, that will change the properties of particle B as well. Okay. So if I have to describe you this with an example, let's say, I mean, if there's an suppose if we have two particles, right, and they're created in such a way that the total spin of the system is zero. Okay, two particles, they are in a system and they are created in such a way that total spin of the system is zero. Okay, now if we are going to measure the spin of one of the particle on a certain axis, and we found that it is moving in the counterclockwise direction, then based on that finding, we can guarantee that the spin of the other particle will be clockwise, or vice versa. Suppose if while making the observation of the particle 1, you found that particle is spinning in clockwise, then the other particle will be in counterclockwise direction. You don't have to measure both the particles there, right? So this property is basically known as entanglement. So there we are exactly not exchanging any information between the entangled particles, but when we are when we are observing one particle, we can predict about the other particle there. Okay. So yeah, so that is entanglement. Based on superposition and entanglement, our quantum computers are built. So the difference between classical bit and quantum bit, like as we in quantum computer we have classical bits, right? The same way in quantum computers we have quantum bits. In classical bits we can store the information just in the form of 0 or 1. And that's our normal computers can understand. But in quantum computers, the state can be basis state of 0 or basis state of 1. The symbol, the notation which you are seeing here is called as basis state of 0 and basis state of 1. When we put a qubit in a superposition state, in that case, the information can be anywhere in between 0 and 1 or 0 or 1 as well. And we only get to know the exact value stored in that qubit when we make the measurement of it. Okay. So yeah, so any questions you have in these two properties first before moving ahead? So how these two properties are getting used, that's the most important question here, right? So when the information we store in superposition state, right, few of the problems can be solved exponentially faster because we just don't have two states, we have n number of states existing for each of the qubits, right? So that gives the like polynomial runtime advantage to the quantum computers here. And with the fact that qubits can be entangled, right, it makes it more powerful in comparison to the classical computer. All right. No questions in this part. Okay, let's move ahead then. So like this, we have different frameworks existing. Like we have Qiskit, we have Pennylane, we have Qiskit is by IBM Quantum Computing team. This is an open source framework which you can use locally on the system, or even you can go to the cloud and make use of it. We have Microsoft's Q Sharp, that is another programming language which you can use to interact with the quantum computers. Then we have Pennylane. We have we have APIs given by D-Wave Quantum Computing, D-Wave company. Then there are a few others. I mean, companies out in the market like Cambridge Quantum Computing. We have Rigetti. We have Honeywell. Apart from that, there are a few startups as well which are developing full-fledged portal. Let me show you a few of the names so that it can be helpful for you. We have QCTRL. Okay, this is like a company founded by one of the researchers from Australia. If you want to know about them, like what they are doing, how they are doing, you can go. So it is a whole quantum system to minimize the noise, hardware error, and make it more stable for making good use of it. And this is getting used by different companies. So this is one of the company. I was talking about D-Wave as well, right? So D-Wave is like they are in the market from quite a long, and they have developed their own quantum computers. This also you can use based, I mean, by interacting with their API. So they have well documentation available. Okay, so if you want to learn more about the solution and product, or if you just want to learn, you can just go to the learn. You can start with quantum computing or any of the application. You can have a look at what publications they have done, or resource library you can look at. So if you want to look at resource library, for example, you can go there. There would be different case stories which they have worked with different companies on different industries. So if you see the use of quantum computers these days, right, it is getting used in finance industry for portfolio optimization. In automobile, it's getting used, right, for automation, mobility. Companies like Volkswagen, BMW are also using for manufacturing and logistics optimization. Then for like traffic signal optimization is one of the use cases which people are working on. Then drug discovery, molecule simulations, and apart from that, material discovery. There are a number of use cases which people are exploring. Then quantum machine learning, what we are going to talk about today, right? There is like you can train a model in such a way that it can be a hybrid of both classical and quantum computers both. So by hybrid, I mean like few of the part of that. Few of the part you will solve on classical computer, and few of the part you will solve on quantum computer. So these kind of hybrid architecture is also being developed. So yeah, I mean, you can just go through these resource libraries. It will help you out to understand more of the use cases and areas of your interest, like what you like to pursue further in the, I mean, as a researcher. Okay, so I mean, yeah, coming back to IBM Quantum Computing. So Qiskit is like one of the software development kit, a framework based on Python, which is being developed by team. That is open source and free to use. And even if you want to try your hands on actual quantum computers, you can go to quantumcomputing.ibm.com and can sign up for can create your account. Then you will get a portal like this. If you're programming locally or on some other ID other than this cloud portal, you have to make use of your API token, and you can code there. We have IBM Quantum Composer as well. So if you want to make use of that, you can go to Quantum Composer. It has a drag and drop like gates given. So there are different gates available. Hadamard gate is the one which is responsible for putting your qubit to the superposition state. And there are multiple gates as well. Like in one session, we cannot cover each and everything, but just to introduce you to the topic, to the environment, I will just touch base here. So if you want to, so this is for the measurement of the value on the from the quantum bit, from the qubits. So always whenever you're designing a circuit, right, there should be some classical bits or classical registers as well, because measurement, right, you want to store that information on some classical register. You cannot get the value without measuring. So for that purpose, we make use of classical register. So we have applied Hadamard gate here, we have applied C0 gate here. Then we are measuring the value of Q0 and Q1. And whatever the observation is that has been plotted here, the probabilities of a particular state has been plotted here. And this is block Q sphere, you can say, in which we have demonstrated the state of that particular qubit. It is in the basis state 0, 0. All right, so this is the low-level code, which we code in Python that gets converted to this kind of form. If you see Q register is for quantum register, C register is for classical register. Then we are applying Hadamard gate on qubit 0. Then we are putting C0 gate on Q0 to Q1, and then we are measuring the value of both the qubits. Okay, so coming back to this, so this is one of the way you can design your own circuit. We have online composers as well, like a notebook-like environment. If any one of you have tried your hands-on in data science IDs like Jupyter Notebook or Spider and all, so this is online hosted Jupyter Notebook environment by IBM Quantum team, where you can just start importing the Qiskit package and start working on it. Okay, so people who are starting with quantum computers, Qiskit is like one of the good framework to start with. It is well documented. It is open source. You can contribute to it. If you're good in coding, if you want to implement some new tutorials, or if you want to make use of the quantum computers provided by them, you can always reach out to the team as well. I will show you how you can apply for the researcher access as well. So if you want to get started with it, right, you can go to Qiskit tutorials, or you can go even to Qiskit.org. So they have very well documented all the functions, and they have even demonstrated the use case of it. You can go to this and you can start with the documentation. When you open documentation, right, from very basics to the advanced version of the Qiskit, they have explained. They will give you introduction, how you can contribute, how to configure it locally, then API references and all. So you can start with any of this. Suppose let's start with introduction to Qiskit. So this is like one of the documentation page. It has been developed by them. So they have clear explanation how to build, compile, and analyze your results, how to code, what line of the code is performing what operation or what action. All this has been demonstrated. If we just take this basic example, right, how we can do that. So if you see here, we are importing the NumPy as a package. Then we are importing quantum circuit and transpiler from Qiskit. Here is a simulator. From that is a similar simulator element from which we are importing Quasm simulator. And visualization is for visualizing the output, what we get after running a circuit on simulator on actual quantum computer. Then we have created an object of Quasm simulator. We are creating a quantum register here of 2 qubits. Okay, then we are applying Hadamard gate on 0th one, and we are applying a C0 gate. I will walk you through what is the purpose of Hadamard gate and C0 gate or control NOT gate. Then we are making the measurement of this from qubit 0 to qubit 1 and qubit 0 to classical register 1. Qubit 0 to classical register is at the 0th index, and qubit 1 to the classical index at the 1th index, like that. Then we are transpiling the circuit. We are running that on simulator. We are getting the result in the job. So by using the result method from this object, we will get all the results. We are getting the count of after execution, and then we are just displaying that. So since this current circuit is running on the simulator, that's why the error induced to it is very low. If you see, both are approximately same, the 0, 0 and 1, 1. If in case if you're running this on actual quantum computers, in that case, the error rate can go high. And in between, so when we have a 2-qubit system or 2-bit system, right, what all possible states can be there? It can be 4, right? It can be 0, 0, 0, 1, 1, 0, and 1, 1. But since we don't have any error induced to this one, because we're running on simulator, that's why we just have 2 states, 0, 0, and 1, 1. if when you run this on actual quantum computers, you will be getting other states as well, which they have not demonstrated in this. But yeah, we can try hand on that as well. So coming to back to this, so if anyone wants to get started and learn more about that, you can go to the documentation of this, and they have given tutorials, applications, what all areas it can be used in a detailed explanation along with the code. So it's a self-paced thing which can be easily understood. So let's start with circuit basics here. So if you see all the basics about the circuit, they have given on this page, right? If you want to go through the use cases which have been developed using Qiskit, then I mean, these are algorithms which are being implemented: Gover's algorithm, Shor's algorithm, which I was talking about. Right? So Shor's algorithm basically make use of quantum Fourier transformation and quantum period finding. Using those two implementation, using those two algo, it is demonstrated to break down the RSCs. So apart from that, if you want to look at the applications in different sectors like machine learning, or its application in chemistry, physics, or biology, its application in finance, or any of the optimization problems, right? So you can go to the application part of it. You can let's start with machine learning only. This is what our session is focused on today. So a brief index has been given here, right? How to get started, installation, API references. So there's a separate Qiskit machine learning library module for this, which you can refer to. And they have also demonstrated few of the tutorials as well, like quantum neural networks, neural network classifier integration, QGANs, and how to make use of hybrid approach, where they have tried using PyTorch and quantum neural networks for solving for basically predicting handwritten digits. I hope many of you will be aware of MNIST dataset that is composed of digits from 0 to 9, and those digits are handwritten. The images of those are available as an open source data set on internet. You can look on that on Kaggle or some other portal. So using that, they have demonstrated the use of quantum neural networks and all. Like, let me see if this tutorial is based on that. No, actually not this one. We can see this one. Okay, so here they have demonstrated simple classification and regression techniques, how in combination with PyTorch. So if you see, right, in quantum neural network as well, we are doing feature mapping by applying ZZ feature, ZZ feature map, and by changing the amplitude of the qubits, we are training the neural networks here, right? So this is how your architecture will look like. Then some optimization implementation is also there, where we make use of any of the loss function, right, to optimize the parameters of the circuit. Then the evaluation part of it. I mean, don't worry, we will walk through in detail through one of the tutorials, but just this, I'm introducing you to this, like you can understand what all options is available to you apart from classical machine learning and deep learning techniques. So Qiskit is one thing, okay? Apart from Qiskit, if I have to show you a few more things. So they have their own Slack channel as well. So Slack is a community, Slack is a, you can say, a communication app kind of software, which is available as an app on your mobile phone as well, and you can use that on system as well. So I have also installed Slack and Discord servers. Okay, so you can join the Slack community of Qiskit, and there, if you're getting started, it will be very helpful. People are always open to help out with any kind of questions or doubts you have. So do join this community as well. Not just this community, any of the any of the communities are interested in, right? Whether it is of Qiskit or offered by Pennylane or some other communities relevant to your interest, please join them, because people are helping each other out and learning together. So here, if you see, right, they have classified the MNIST data sets using the hybrid approach of quantum neural networks. So they are making use of PyTorch here. So from Torch, they are loading the data, they are transforming the data, they are importing few of the layers, neural network layers like convolutional 2D layers, dropout layers, flattening layers, max pool layers, sequential layer, and all. The optimization function also have been the activation function is also being imported in rel. Okay, and based on that, I mean, in this step, if you see, right, we are loading the data set. Loading is very common, like dataset.amnist. So that comes, you can directly load it from the PyTorch, or even if you have a CSV file, that also you can do. That's up to you how you want to load the data and transform that. Once the data set has been loaded and been split into X train, train and test data, right? So you can plot them out. So here they have demonstrated few of the labels. So in this tutorial, they are just going to classify whether a particular image is being labeled as 0 or 1. Okay, so that's why they have filtered out the data, and they are just training a hybrid neural network model based on these two images. If you want to scale these up for multiple images, that also you can try. Then test data set is here. Okay, from the same function, they have imported the test data. Then they have defined the QNN and hybrid models. If you see in this part, right, obviously the quantum cannot take the data what we have, right, and even the dimension of the data set or the size of the feature size which can be fed to the quantum model is very limited. Okay, so either you can use some PCA techniques to reduce for dimensionality reduction of the data. Quantum PCA implementation is also out there. You can quantum PCA. Let me show you the papers. Okay, so whatever like classical machine learning algorithm are existing these days, right? People are trying to find it or do the implementation of it at least on quantum computers as well. I mean, so far we were just using PCA, right, for dimensionality reduction. So Shanhei and Jan and Li, Liu, all, I mean, these four researchers basically they gave in 2020 they proposed quantum PCA algorithm that is like one of the state of the art for dimensional reduction. So if anyone is interested, you can explore this one as well. All the links I'm sending you in the chat. Oh, Qiskit.org. Okay, that's it. Okay, so coming back to this, so feature mapping, like how to encode the data to the quantum data format is most important here. So here, if you see, they are making use of two qubits like Q0, Q1. They are using ZZ feature mapping here and real amplitudes, like whatever angle you want, whatever amplitude you want to keep for those qubits has been handled here. Then we have normal PyTorch architecture here, in which you're putting up convolution layer, linear layer, dropout layer, and all. And then we are also applying max pool layer, value activation function we are applying, and like this, the whole architecture has been created. So this is the module which is of the classical part. If you see, so this from here the two-dimensional data, whatever you're seeing here, right? So initially, when we will start with when we start with designing the architecture, right? So this is your whole architecture, for example. Okay, and here we are training the feed-forward neural network. I know this is a bit of complex, even though if anyone of you are not aware about the deep learning concepts, but I mean, grasp whatever you can, take it as a base for learning here onwards about quantum machine learning or quantum neural networks. So in this, if you see, right, initially we defined a convolutional neural network and the kernel size we have given 5. Then these 3 are also convolutional neural network here, right? So the dimension here would be like 256 or 64. Then we are again dropping out the feature side, and we are converting this to two-dimensional input to QNN. Okay, so the output which we will be getting from this fully connected layer from here, that will be passed to the QNN layer what we have defined above here. Okay, so QNN4 object we are passing for this torch connector, right? So here at this layer, your neural network will be at this step. Whatever will happen on the quantum computer. And again, at this step, whatever output we will get from this layer at this step, that will be passed to this. And finally, we will be getting the one-dimensional output from QN, predicting whether, based on the probability, whether a particular image belongs to the 0 class or 1 class. Then this is the feed-forward. I mean, here we are training feed-forward architecture, right? So the architecture has been defined here, like at what step what input should pass in. So here we have initialized like this, And if you see, all the layers are being passed to, like, we start from here, then the output of this layer will be passed to the next layer, and so on. It keeps happening. And finally, we get the output here. When we created the object of this architecture, right, next we have to train the model. So for training the model, if you see in this case, we are making use of Atom Optimizer. For Atom Optimizer, those of you who don't know for what purpose it is being used, let me show you from here. Okay, so the full form for Atom is adaptive moment estimation, is an algorithm for optimization technique for gradient descent. So it's make use of gradient descent, and it optimizes the parameters there to, so that the neural networks can be trained efficiently. Meanwhile, I will take a pause. Any questions you have? No questions. All right, let's move ahead then. Okay, so yeah, so this optimization function will be basically used for optimizing the parameters in the hybrid architecture, the combination of the classical deep learning architecture and the combination of quantum neural network. The architecture which you have designed will be optimized using this optimizer function. Okay, then based on the loss function, we are trying to calculate how well our model is getting trained. And I mean, we have trained this for 10 epochs, I think. Yeah, number of epochs is 10. So most of the things are similar to the, so is the module related to simulation modeling? Simulation of what, Apoorv sir, if you can give a bit more of information. Okay, so yeah, coming back to this. So once the model has been trained, right? So if you see the loss function is started with -67 and it goes to -1.4596 for the 10 epoch. And if we plot the negative log likelihood loss, you can see the convergence of the hybrid neural network architecture here. And when you evaluate this model on the test data set, in this tutorial with this code, we were able to find accuracy of 70%. Obviously, with the classical deep learning techniques, right, it is not very much close. People are able to get the accuracy of 98%, 99%, and even 99.98, that kind of accuracy with deep learning architecture. But see the number of qubits also we have used here, right? If you are training such architecture on using classical deep learning techniques, we make use of all the features available to us, right? But here we are just making use of 2 qubits in between, which is going to get executed on the quantum computer, but still we are able to achieve an accuracy of 70%. There are a few other data sets which are being used, and with that people were able to demonstrate the accuracy of 80 plus or 85 plus, 90 plus as well. So that's use case basis again. But with more advanced quantum systems, right, it is expected that in near terms, the operations, whatever we are performing on using classical deep learning algorithms, right, those can be outperformed in terms of time complexity using quantum computers, using quantum algorithms. So this is the predicted tables, and you see like this class has been predicted wrong, these 2 classes are being predicted wrong, but I mean, few of the classes are being predicted correctly as well. So I mean, these are more of the coding part. If any one of you want to give it a hands-on try, I'm sharing the link. You can go through this. Coming back to so not just Qiskit and IBM Q, right? I wanted to walk you through TensorFlow Circ as well. So TensorFlow is the deep learning framework given by the Google, right? It is also open source package which we very commonly used for deep learning tasks, whether it is for image classification or natural language processing. In all these sectors, we make use of TensorFlow. TensorFlow Quantum is the quantum machine learning, or you can say quantum-based Python framework, which is built on top of the Cirq. Cirq is the another open source package of framework which is developed by Google Quantum AI team. Okay, so if I talk about this, right, I mean, it is also similar to Qiskit, the quantum computer which is being developed by Google. You can interact with those using this, and even you can run your code on simulator as well. They have also provided simulator. There are different sizes of simulators which are available publicly to us. If anyone of you are interested in contributing to Cirq, like if anyone of you are a good coder and want to dive in the coding aspects of it, you can go always to GitHub, okay, and you can see what all tools have been developed, how they have integrated, what all quantum computers they are making use of, how they have integrated different components from other companies as well in this, right? So installation and documentation, tutorials also they have given good amount of tutorials are available to get you started on this. Apart from that, if you want to catch up and say what is going on with Google Quantum AI team, so they host weekly meetups. Okay, so if you are a machine learning enthusiast, feel free to join TensorFlow Quantum. Not this one actually. So there is a Google group using on which they develop or they host events on a weekly basis on Wednesday and Thursday. One day they do for Cirq and one day they do for TensorFlow Quantum. Okay, so you can join that. Start with a mailing list and see or you can join this Google group mailing list, and from there you can navigate to those communities as well. So there you will have the option to interact directly with researchers and core team behind the development of these packages. And even when I was telling about Slack community of Qiskit, right, they are also the experts and the core development team of Qiskit framework. IBM Quantum team is available on that community portal on Slack basically. So you will be having chance to directly interact and figure out like how you can contribute, what you can do with this framework, how to learn and move ahead in this research area. So let's take you through a few of the tutorials using TensorFlow Quantum as well. Right. So even they have a very nice documentation available. I'm sharing the link in the chat. So if you want to get started with it, always you can. Documentation is the best place to get started with it. On YouTube also you will find different channels for Qiskit and TensorFlow Quantum both, and even for Microsoft Q Sharp as well. So do attend, do watch those videos, do read through the documentation for better understanding of this area, of this field basically. So if I just talk about quantum machine learning part on this as well, right? Let me see where they have given the examples. Okay, I will find that out. Before that, if you, I mean, since I hope most of you are educators, professors, researchers, and shaping the future of education and training students out there, right? So educators workshop is like being designed for professors and trainers. Okay, so feel free to explore these links, see what they have given, what they're trying to explain. If you want to attend any of the Cirq intro workshop, like you can just click there. You can you can get started with that. So this is self-paced tutorials being developed by the team, which you can read and try your hands here. Okay, for running this, you don't need to explicitly install Cirq on a package. If you're not comfortable on your local machine to work with, or there is some hardware constraint, you can just directly click on this button, run in Google Colab. So it will open a colab.research.google.com. It will open the notebook there. And this is also a Jupyter notebook like similar environment. Many of you will be aware of that. You can run the code here itself directly. Okay, so the whole step-by-step table of content has been given here. What is happening, what kind of operations you can perform, how to initialize a qubit in Cirq using Cirq, right? How to name a qubit, how to apply different gates to a particular qubit. All these have been given. So in Circ, we have also an option to name the qubit. We have named these 3 qubits A, B, and C. We are putting qubit A and B in the superposition state by applying Hadamard gate. Then we are applying C0 gate from B to C. Then again we are applying superposition on quantum bit on qubit B here. So like this, n number of examples are given here. I cannot cover up each and every part in this small session, but yeah, you can go through it. Okay, so coming back to Sir's question, like as we do in MATLAB, before defining any model, we need to create simulation technique. Yes, sir. So it is always a good practice, right? Whenever we are going to any of the machine learning models or any of the quantum-based solution, if we have developed, it's always a good practice to first simulate that on simulator. So we have quantum simulators available in almost all the frameworks or software development kits like Qiskit, Pennylane, and all. So first execute that circuit, get the results from the simulator, and then go for executing that on actual quantum computers. Does it make sense? All right. Moving ahead, let me see what else I wanted to introduce you to tutorials and examples. Quantum variational is being given here. Yeah, so you can see that topic-wise tutorials along with the examples they have classified here. If you cover up all this, you will be good with Circ as well. So if I talk about, I cannot see, Shor's implementation is also there, right? Grover search algorithm is also there. I'm trying to show you one of the use cases using quantum machine learning. Let me search like this, QML, using Tensorflow. Yeah, here if you go through. So quantum machine learning module is also developed by, it's being given on TensorFlow Quantum as well. So if you want to go through any of the tutorials, it's a good place to start with. So as I was telling you, quantum machine learning is built on two concepts, quantum data and the hybrid approach of quantum and classical models both. So few of the layers will be trained on classical, few of the layers will be of classical technique, will be implemented on classical data, and then few of the execution will be happening on quantum using quantum data. So the terms and how to design these hybrid models has been given here. So you can just let me walk you through one of more tutorials using MNIST classification only. Okay, so I will just quickly walk you through, not in detail. So in this tutorial, just to give an overview, what is happening is they have again picked the MNIST classification. This data set is of handwritten digits from 0 to 9. And they have filtered out the data for classes 3 and 6. They're just trying to differentiate between whether a particular image belongs to 3 and 6. So loading and all has happened. Then they rescale or resize the features. Okay, then train and test data. And this is your actual image looks like. Obviously, the dimension of the current image is too high. Right? It is 28 cross 28, I think. Okay. So yeah, 28 cross 28 size is there of the image. So further, I mean, we cannot feed that data to the quantum computers, right? So for that, we have resized the image to 4 cross 4 so that we can just make use of 4 qubit system and can train our model. So after resizing that to 4 cross 4 dimension, this is a particular class which they have plotted here. So from a normal human, I cannot also predict whether this is an image of 6 or 3, right? But by just looking at this picture. So, we are going to fit this to the model. We are going to fit this data to the model and see how well it turns up to. So there will be contradictory examples as well in the data set, like a particular image being labeled as 3 and being labeled as 6 as well. So such kind of data cleaning and data preprocessing has been done. Then further, we are encoding the data to the quantum circuits. So we have decided a certain threshold. If the size is greater than that, we are filtering for that. But if we apply that threshold, the number of the images which we are left with is very low here, right? So that's why for now we are not going to apply that threshold limit, because we will be just left with 193 images, which is not like very efficient for training your model. Okay, so this is the piece of the which is responsible for, I mean, basically rotating or converting, mapping the image data to the circuit. So qubits and all has been initialized, and by enumerating through the values, we are mapping each of the values to one of the qubits. So if you see, we have initialized a classical qubit register, a quantum register of 4 qubits, right? And equivalent to that, the classical bits will be also required here. So after creating that quantum register of 4 qubits, we are mapping one. So if you have resized the images to 4x4, obviously the dimension also which will be available will be the same, right? So we are mapping each of the qubit with each of the values, individual values. And when the value has been mapped, the train and test data will be ready. We can plot the circuit like this. So you can see we have 2 qubits, right? And we have applied this Qiskit here. Okay. And for this, what we are doing in this is like we are converting this to tensor. Tensor is again multi-dimensional matrix, you can say. So don't get confused with the tensor word. I hope everyone of you would be aware of that. Then further comes the designing the architecture or the model part of this, right? So this is a class which they have initialized for circuit layer builder, in which they have initialized with how many number of qubits are the readout variable, and then they are iterating through that, and whatever circuit will be built, right, these values can be printed. So you can see, right, they are appending with prefix, hyphen, and so on. So all these values you can see in the circuit which you've designed here. So SymPy is basically used for creating these kind of symbols here. Coming back to circuit layer, right? So if you see, they have passed the circuit data which we have created above, and read out to which particular grid the data should be read out. So if you see, we have 4 qubit system, right? So in this, this is the demo layer which has been built, okay? And on this, we are applying Qiskit, if you see from here, for each of the values, and then we are appending gates and read out along with the symbol here. So whatever values we are going to read out from this quantum part, that will be measured classical registers here. So this is just 2-layered model for matching with the data circuit size, and it includes the preparation and readout operations. But in between, there can be many other operations also which we need to perform for getting better accuracy. So a few of the more layers are being added here, and like access gate, ZZ gate, and all has been applied on this. If you see, H gate has also been applied for putting the qubits to the superposition state, and while reading out also we are applying as H gate and then measuring the value of it. So once the model has been model architecture has been built, right? So that will be passed to the. I mean, we will build a sequential Keras model in which we will take the input of the data, and then rest of the piece will be executed on the like. So PQC stands for parameterized quantum circuit. Okay, here it has been given. So in this layer, we will pass the above architecture, model architecture, whatever we have created in this. All these layers will be coming at this step here. After that, we will be, I mean, they've just defined an metric to like see how well, how efficient our model is getting trained. So here they are considering hinge accuracy, like which handles the value between -1 to 1. Okay, and yeah, based on that, the model will be compiled, So we have loss function as this hinge. We have optimizer function Adam, and the metrics which we are going to use for the evaluation of the model is hinge accuracy. So this is our model architecture. Like we have input parameterized quantum circuit layer, in which just by making use of 32 parameters, we are going to train the model. In real-time scenario, these parameters goes in millions or billions as well, depending upon the size of the data set, which we are going to use for training the model. In the next step, we are training the model. We are just going to train for 3 pods, 3 iterations. Batch size, the number of images which are going to get processed at one time is 32. So yeah, so here by calling model.fit, by specifying the data and all, train data, test data, and epoch, verbose, validation data also we have passed in here. Gets trained for 3 iterations. And if you see in 3 iterations on this data set, validation accuracy was close to 89%. Loss function was 0.37. And validation loss was 0.35. These are pretty much close. So we can say that the data is not overfitting or underfitting here. And yeah, so if I move forward, right, the classical neural network also they have trained here. And in this, if you see, this is a fully connected layer. And the accuracy which they were able to achieve from this fully connected deep neural network model was 99%. Okay, and they just trained it for 1 epoch. And when the model was evaluated, the accuracy was again 99.9%. But this model was trained on 1.2 million parameters, which in comparison, like 32, but in quantum neural network model, what we saw here, right, we just used 32 parameters for training the model. So if we bring down our classical deep learning architecture as well on close to the same number of parameters, like what they have done here in this code, they were about, they got the accuracy of approximately 91% after 20 epochs, right? And with by the use of, if we executed that on classical, we were able to get the accuracy of 89% with 32 parameters only, right? And the number of epochs were also less, just 3. So with this, if we make the comparison of the hybrid architecture which we executed on quantum computers and classical computers, and the one we just directly executed on classical computers, we can say, right, the quantum computers are very much closely performing to deep learning architectures, classical deep learning architectures. And in near terms, if we have more advanced quantum systems and a better way to handle the noise within the systems, or more better hardware we can come up with, it can easily outperform the classical deep learning techniques. See, I mean here, this accuracy you're getting after 20 epochs, and this accuracy we're getting after 3 epochs. So that sort of advantage we are getting using the quantum, basically. Okay, so before moving ahead, any questions or any use case you want to talk about using QML or QNN? How many of you are getting introduced to quantum computing for the first time? Most of you, right? And does it sound fascinating and interesting? And can you observe this promising in near term future? Right. So yeah, that's what I wanted you to bring on. I don't expect that everyone would be able to understand all the concepts. Still, I'm trying to learn and understand and gain more and more expertise in this area. And it's really going to take a lot of time. Can we apply quantum optimization to numeric data? Rachna ma'am, what kind of optimization? Yeah, I mean, numeric data, at the end, whatever features we have fed in, right, those were in the form of numerical values only, right? I mean, we cannot feed images directly to classical or quantum computers. So first we create the feature vectors from the images. Features are the numeric values only, which we further pass to the quantum. Okay, so now let's talk about, we have 20 minutes left. I wanted you to introduce to the research opportunities available for you all and how you can make use of several educators and researcher programs available for the especially for the faculties and professors out there. Okay, so let's start with the quantum part only. Let me take you to this IBM Quantum Lab. Okay, so if any one of you have any use cases in mind, and before let me explaining you this, before that, let me show you research areas in quantum machine learning first. So people are developing Bayesian optimization algorithm on quantum, and there are many other use cases as well, like improving the existing neural networks. So let's go through this once. And yeah, Pennylane also I wanted to walk you through actually. Yeah, so you can see, right, what all companies and universities are focusing on quantum machine learning. University of Waterloo is from Canada, and Nathan from Microsoft, and Shian from Intel. They are working on focusing on quantum machine learning, and they have given some algorithm for damage reduction as well. The implementation of this also you can find somewhere, or you can even directly just approach to these researchers for the work. So this is like one of the link you can explore what is the existing work happening in the area of quantum machine learning, and as a researcher, what you want to do, whether you want to be at the code development side of these QML field, or you want to be at the applied side of this, that you need to decide. People are making having a look of this at the applied side as well, on the image data or in numerical in any of the structured numerical data as well. Okay, so this is one. Let me show you a few more. So this all we have already discussed actually. Okay, so this is like one of the good blog to give you a brief understanding about what is happening, what people have worked on, what problem they are trying to solve. So this link also you can have as a reference. Apart from that, if you are really into research field and all right, and if you want to read existing work, search for quantum machine learning papers, and a good amount of research work you will find on archive, Google Scholar, ResearchGate and all. So I mean, this is also one of the best place to find the research papers, archive, ResearchGate, and Google Scholar website. So you can see, right, what all work has been done. If we sort, let me see if yeah, it is already in US first. So large scale, how now people are also working on scaling quantum machine learning for large solutions, right? Time series processing, neural networks for classical data classification, and number of areas are there to contribute and work on. Okay, so if you have some ideas in your mind and you want to assess more powerful quantum computers, in that case, let me show you this link. So, not this one actually. Yeah, yeah. If that is there, then what you can do is, ideally we don't have like um, powerful like quantum computers with high number of bits open to us, right? Max, I think just 5 qubit systems or 8 qubit systems are publicly available to us. So if you see, if you go to this link, right, you can see all the quantum computers available. So it is available in Montreal, Kolkata, Mumbai, Manhattan, Dublin, Toronto, Sydney. And if you want to check, 27 qubits systems are there, 65 qubit systems are there. right? And I think 65 qubit system is like one of the most powerful quantum system provided by IBM Q. But that is not publicly available to us. You can see this lock button at the top right. We don't have access as a public. So if you click on any of these, right, you can read at the description of it how the qubits are arranged in what architecture, what is the error rate, readout error or CNOT error, and what is the processor type, how many number of jobs are pending on this. Number of pending jobs shows that people are working and researching on this and doing some use cases, trying to solve some use cases here. But the ones with the unlock button are publicly available to us, and we just have access to the 5 qubit system as a public, right? So as an educator or as a researcher, if you need more powerful quantum computers, you can always reach out to them and request for that. I will show you how. Before that, let's have a look at the simulators as well available to us. So these are the simulators. So instead of directly running your solution on actual quantum computers, you can make it first run on simulators and then change the backend. So let me show you this part first. Docs and tutorials. Let's go to the home page. Okay, so here if you see, right, we have researchers program and educators program. So as a faculty, as a professor, you can always apply for the researchers program. You can fill in your details here. Mention the institute name, department, when you're planning to teach this course, what is the course you want to train them on, syllabus if you have designed based on the Qiskit documentation, what all you want to teach, and how do you plan to integrate IBM Quantum or Qiskit in that. Submit the form, their team will reach out to you and will help you out with resources and setting up. And they also train educators and faculty separately. So it's always a good place to get started a conversation with them. Next, if as a researcher you want to do some sort of research in any of the areas, right? So this is the link which you can go through. You can fill in your details. You can explain in few words what is your research plan. You can select the field of the research. Based on that, their team will get back to you. You have to estimate the number of resources you're going to use, like what size of the qubit system you want to access for your research work. Propose to them, and they will unlock that quantum system for you. So that will help you in speeding up your research work and finding something new in that particular area. So this was about IBM Q. Any question from the IBM Q portal? I wanted to introduce you to 2 or 3 more portals. We have 10 minutes left. Let's see what else I can do. No questions. Please ask questions. It can be anything, QML, ML, DL. If you have any ideas, we can talk and try to validate if it can be done or not. If I have the knowledge, I will try to do that. If not, maybe I will try to find the answer and get back to you. All right. Another portal is another framework actually is Pennylane. Pennylane AI also is like one of the framework which is being developed by Xanadu. And here also you can find good amount of documentation, and they have been providing support on AWS. They've also integrated Qiskit. They have integrated Tensorflow quantum or Circ framework. They are making use of Rigetti quantum computer, IonQ quantum computer. They are making use of a hybrid approach, and all we need PyTorch and TensorFlow as well, right? So they have integrated that as well in their library. So these are the few of the tutorials. Pennylane is very much commonly known for machine learning problems. And Maria Should, I don't know how many of you know her. So she's the one who is really doing, I mean, Pitek is one of the scientists. His tutorial you can find on YouTube, okay, to get started with machine learning. But she's also like, has done a good amount of work in the field of quantum machine learning. So if you want to see what is happening recently in the field of QML, right, please follow her. You can add her on LinkedIn as well. Check out her Google Scholar profile, or you can even connect with her on Twitter. And if you want to read the book which she has written, Supervised Learning with Quantum Computing, that's a good book actually to start with. Supervised Quantum Machine Learning. So from very basics, she has started the touch base, and then she moved towards the implementation on the quantum computing side. Apart from that, we have, I'm sending you the search query link, or let me send you her Google Scholar profile, actually. It will be more helpful. Okay, so see the amount of papers she has produced and how many times her papers are being cited. So yeah, she's the one. Then Peter Vitek, QML tutorial. All right, so I mean, these tutorials you can basically follow to learn the basics of QML and quantum computing. So this is also one of the good resources to get started with. Oh, sorry, I've sent you the wrong message actually. Copy link. Okay, and if you want to go through the free open source available online, you can always refer this QSF. QSF stands for Quantum Open Source Foundation. They support like enabling others on quantum technologies, quantum machine learning technologies, and even they host internship kind of thing, you can say, where there would be few mentees and there would be few mentors. Mentors would be mentoring the mentees on a few of the specific areas on QML or quantum computing. Okay, so you can have a look on their website, QSF. Let me see where they have mentioned the website link. Yeah, qsf.org. Okay, so this is like one of the connect with this, and also you can connect with them on the Slack community here as well. And you can see that QC mentorship program, someone is getting started with it, how to do that, get a proper mentorship, all these options are available here. You can also apply, if you're already a researcher in this area, you can apply for the prizes, you can request for the grants as well if you're working something openly for the community, all these things. Coming back to Pennylane, right? So they have full QML module available. You can go to this, what is QML, key concepts which you need to learn about quantum machine learning, demos along with the videos are available on this link, and this is a good place if anyone wants to directly start with QML. But I will suggest first go through the Qiskit basics and basics of the quantum computing, and then try your hands on, like without understanding the basic concept, basic algorithms which are being implemented on quantum computer side. Understanding more complex topics will not be the right choice there. Apart from that, Qiskit has also given a course, Introduction to Quantum Computing, which if you want, you can search on the YouTube channel. Yeah. So if you want to request for 3 credits from other quantum computing companies, right? INQ, I mean, most of the quantum computing companies are like, they have paid programs for their partners and for the industry people. But as a researcher, if you want to get credit based on the use case you're going to work on, you can always request to them. So they're also providing $10,000 free credits to work on their quantum computers to qualified academics. Okay, so you can propose like what work you want to do, what is your research proposal, submit your work here, and they will get back to you. All right, apart from that, we have AWS Bracket as well. So AWS Bracket is online cloud service, quantum cloud service provided by Amazon, and even they provide access to researchers and academics. If anyone of you want to collaborate with them, with any of these companies, actually, not just Amazon Bracket, even with IBM, or even with Amazon or INQ or Rigetti or D-Wave, feel free to reach out to them, and they will be, I mean, you can collaborate at the institute level as well, and bring quantum computing technologies to your institute as a researcher or as a faculty to train the students. All right. So with this, I think I'm almost done. Most of the aspects of this I've covered. One more thing I wanted to show you. So people like they would be doubt, right? What is the like? These are the companies which are focusing on this in academia. What is happening? So if you want to see the open position in the field of quantum machine learning, let's have a look at that as well. PhD in quantum machine learning. So these are few of the research positions at the doctorate level, and even there are many research positions available at the postdoctorate level as well. So you can go to the websites like academic positions, find a PhD and all. And I think many of you would be already aware of all these websites. You can search and apply to any of the institutes. So it's like this is one from one of the smart group in France. That is when it was being posted. Let me see. Yeah, so this is like one of the PhD position open like that. If you go to find a PhD, right? This one. So there are enough number of doctorate and postdoctorate positions available across the globe. So you just need to find the right fit for you, like where you want to go and what is your aspiration for the university, if anyone is looking for, and you can start your application process as well. Most of the PhDs are like a funded one, and they provide full support. There, I mean, even the stipend also are good in comparison to India, what they pay outside. And one is Marie Curie Scholarship in quantum computing. So you can also search for this, and there are several research positions and open under this Marie Curie Scholarship as well. So I'm posting a few of the links in the chat. You can keep it for your reference, or you can just Google it. Or if any one of you are missing out any of the links or not able to follow up along with me during this session, please feel free to reach out to me. I will share my contacts here. So this was just an introductory session for you to introduce you to the work, what is happening, what has been done, what you can do in this area. Many of the topics I had to skip, seeing the time constraint. Okay, so this is my contact details. Either you can WhatsApp me, or you can drop me an email, or you can connect with me over LinkedIn. I will be happy to collaborate at any capacity, whatever is possible for me, and can guide you with right resources or help you in upscaling in these technologies. You can also reach out to me for machine learning or deep learning as well, if you need somewhere.
Participants, kindly mute yourself. And if you have any other questions,
Qiskit link which you want to share. Yeah, so let's take a question in next few minutes. Any questions or anything else you want me to introduce you?
yeah, Shadab, I have a question. Can I ask?
Yes, ma'am.
Yeah, when we talk about these quantum computing and all that, but this is something in parallel to this, not exactly I am talking about quantum, but generative adversarial networks.
Yeah, GANs are there, ma'am.
Okay, fine. So but again, it has many of the challenges.
Yes, ma'am.
Yeah, so can you just put certain highlight on that also?
Okay, so ma'am, GANs is like based on deep learning concept, okay? Yeah. And there we train basically two models there, right? If you have seen the architecture of it.
Yes.
One is based on the real images, one is based on the fake images. Mm-hmm. And so there we have a generator and discriminator, right? Yes. So if the optimization function, and I mean, basically the architecture there is not designed properly, basically the discriminator one. And if you're training the model, even the fake image is getting trained as a real image. So obviously the chances of getting the wrong output will be very high there. So, I mean, this in whole is I mean, this is, you can say, how you optimize your code there, the optimization functions and all which are using, making use of it there, right? And how you design your generator and discriminator, it totally depends upon that, like how your GANs can perform on some like real-time use cases.
Yeah, but still, like it is in use and it has certain research areas openings, like for
GAN also,
Yeah.
if you want to search, let me have a look at that, because GANs I explored almost a year back. GANs. Let me search like this. PhD. Okay, so if you just search like this, so I mean, yeah, this is like one of the research area. If I talk about this, right, a good amount of work is happening in this also, and you can go for doctorate or postdoctorate level in this.
Okay.
But I mean, more than this, people are. I mean, there are different applications of this. If you see, I don't have much knowledge in the field of GAN actually, so I cannot comment much. But just from the Google Watt table, we can see like for outlier detection how GANs can be used, and few of the advanced topics in GANs. Let me show you from here. Like, it would be easiest, like what work is that. Papers with Code. Anyone is aware of this website? So this is a website where you can find the paper along with the implementation of it.
Okay.
Okay, so if I search for GANs, right? So a good amount of research work which has been done, we will be able to see. And then you can see like what work has been done. The implementation also can go to the code and can check out. So these are a few of the works from 2017. The few conferences which you can follow for the recent research trends in deep learning and machine learning is ICMA. Okay, so I mean, there's all the latest work, international conference on machine learning, whatever is happening, right? People go and present this. So this is one of the very niche conference in the area of machine learning and deep learning. And another one is Neuro IPS actually. Neuro IPS 2021. So for this, ma'am, maybe like if you have a look on these websites, right, that will give you the recent updates, like what people have worked on and what is happening.
Okay. Fine. Yeah.
Yeah.
Fine. Thank you. Nice information, Shana. Yeah.
Thank you, ma'am. So apart from that, like if any one of you just want to go with machine learning or deep learning research field, right? So there are like almost every universities are offering research work in that. Let me. Why I'm not able to edit this? Actually, I wanted to send the link in the chat, but not able to do that. But you can go to Neuro IPS 2021, nips.cc. Okay, and you will get good amount. Oh shit, this one actually. So you can see what all people have worked on, what are the publications, and all the aspects. The previous historical conference also you can see 2019, 2020, and all. And if we have to see the whole program, let me show you from here. Do that. So universities like CMU, Stanford, and Purdue University, Yale University, and in Germany, if I talk about, we have TU Berlin, LMU. Then we have TU Delft. In in UK we have UCL. All these universities are top notch for the field of ML and DL, especially Yale, Stanford, and MIT. All these. So, I mean, even I'm trying to apply for PhD as well. I have planned to go this year, next year mostly. So, if anyone of you want to apply for CMU, PhD, or postdoctorate in CMU, the applications are going to open soon. You can have a look at that and can apply there. So, Carnegie Mellon is like one of the good universities for doctorate and postdoctorate. And apart from that, research grants also you can apply separately for PhD. So the Marie Curie scholarship, which I was telling you, right? That also you can apply there. So there are different kind of scholarships available. And if I have to highlight few more things in that area, very first one, you can have a look at Marie Curie scholarship in machine learning. Okay, so there are open positions in that area as well, where you can go and apply. Then there are a few fellowships which are being just awarded to doctorate and postdoctorate. And these fellowships are being offered by the companies like Microsoft, Facebook, Google, and all. So if you really have a good research idea, right? So these are the fellowship positions which I'm talking about. You can go to their link, see the application criteria and what all information you need to submit there, and feel free to apply there. So, I mean, this is like one of the good grants and very prestigious to get in. This is very highly competitive as well. Similarly, we have Google PhD fellowships. Okay, so these are the links I'm sharing you in the chat. Make a note of this. And then we have one by Facebook as well. So Facebook is one of the leading organization also in the area of, I mean, Facebook, Amazon, Google, and Microsoft. So they even support researchers as well to scale up their findings and help them out with resources, with mentorship, with grant supports and all to carry out the research work. So you can have a look at this. Like I'm not at that level to comment on this. Based on your interest, you can explore these links and see if this sounds interesting to you. Please feel free to apply. This is really game changing in the field of career in your career. All right, so that's it from my side. Any other thing? Any other questions we have? I have already exceeded the time by 8 minutes. Sorry for that.
Maybe there is no question, Shadab, now.
Okay.
Yeah, thank you, Shadab, for your wonderful session and for the nice information and sharing with our participants. Definitely, it will be helpful for their research work. Thanks one again.
Thanks a lot, ma'am, for giving me the opportunity. And I hope, like, at least if you also will go ahead and research about quantum machine learning areas, right? That will be a very good field to start with, and that will give you lead in upcoming features because you will be the expertise in that area since you started working early. So whenever we start working on some of the technologies, right, there are few early adapters of those technologies which becomes the lead in that industry. So if someone is starting now, you can be at that verge to having the benefit of that.
Okay.
Okay, so thanks to you all. It was really nice speaking with you all, and thanks for bearing me for next 1.5 hours. For the past 1.5 hours. So thank you. Bye. Thanks, Amit ma'am, for the opportunity. Okay.
Yes, thank you, Shadab, and thanks for joining and giving various research areas, the openings, of course, the scholarships, the fellowships. So very knowledgeable session it was. Thank you, Shadab, once again. Yeah.
Thank you, ma'am.
Yeah. Right. So, yes, over to you.
Tomorrow session will be start at 10 o'clock.
Kindly fill up all those feedback forms. That is also considered as your attendance. So kindly do it. And we are meeting tomorrow at 10 o'clock. Thanks. Thanks a lot. We can end up the meeting. Yeah.
Ma'am, where can you get the entire schedule till 6th agenda?
Already we mailed you, na, you people, through the mails and in WhatsApp. And in WhatsApp group also it's shared, complete schedule of the 6 days, 5 days. It's shared with you.
Will you please share it on this chat, please, ma'am? It's possible.
Yeah, or on WhatsApp group, we can share it again.
Yeah.
Yeah, on WhatsApp. Yeah. So you are there in one of the groups. Yeah.
Thank you, ma'am. Thank you.
Yeah.